Hello everyone. Hello everyone. It's a pleasure to be here at the Ideathon 2024. So our research idea is transparent decision making for electric vehicle routing. Together with my colleagues Eli, Iman, Jeremy, Mam, and Suleiman, we want to conduct a comparative study of different models using RL, GNN, and XAI techniques combined together to address these routing challenges. So climate change is one of the most pressing issues of our time. Global temperatures are rising at a fast rate, causing damages everywhere. One of the main reasons is the greenhouse gas emissions caused by industries and transportation. For instance, the transport sector is considered for a significant portion of global CO2 emissions. One of the envisaged solutions is the transition to electric vehicles, which represents a key solution for reducing dependency on fossil fuels and greenhouse gas emissions. This is not just an option, it's a necessity. However, there is this anxiety with EVs due to their limited battery range and long charging duration. And this is where electric vehicle routing problem comes into play. It's an optimization problem that aims to determine the most efficient route for a fleet of electric vehicles. It's a variant of a vehicle routing problem, which is a generalization of the TSP. Similarly to VRP, we want to visit all destinations or customers' locations in the case of commercial fleets within a minimum of total distance, within a specific time window for each customer. Additionally, VRP considers constraints related to EVs like battery limits and charging stations availability. And if possible, we want to minimize the number of vehicles dispatched. All the references we used are listed at the end of the presentation. So how do we solve this problem? Traditional routing algorithms have been effective for simple routing cases, but they fail as the problem size grows. There was this study by Lineal that showed how heuristics, for example, fail to find any solution for instances with more than 30 customers. And this is where reinforcement learning shines. RL is a type of machine learning in which an agent learns to make decisions by interacting with an environment and receiving rewards or penalties based on its actions. It's inspired by behavioral psychology, where agents learn to achieve goals by maximizing rewards through a process of trial and error. RL has emerged as a powerful approach to solving complex sequential decision making problems. Each decision an RL agent makes affects the next decision, and so on. A famous example that illustrates the potential of RL is AlphaGo, the AI that famously defeated the world champion Go player Lee Sedol. AlphaGo excelled at this because Go, like many real-world problems, is about making decisions over time, considering not just the immediate consequences but also the long-term impact. However, during AlphaGo's second challenge against Lee Sedol, AlphaGo made its now legendary 37th move, a decision that surprised both commenters and Lee Sedol. It was a creative, unpredictable move that shifted the game in AlphaGo's favor. However, the logic behind this move wasn't clear, even to its developers. Even David Silver, one of DeepMind's lead researchers, admitted that he didn't fully understand why the program made such a choice until after he investigated the program's inner calculations. This brings us to a critical issue. As effective as RL models can be, they often function like black boxes, making decisions that are not easily interpretable to human users. Now imagine this kind of AI being used by non-experts in everyday applications without an ability to explain its reasoning. This lack of interpretability is a major concern, particularly in safety-critical applications like EV routing. Explainable AI is a key to addressing this challenge. XAI helps break down AI decisions into understandable explanations, making it easier for operators, drivers, and fleet managers to trust the AI's recommendations. Even for us AI developers, when optimizing the model output, we no longer need to wonder if it's a problem with the fine-tuning, or maybe the architecture, or is it in the definition of the state and reward. But even if we add a layer of explainability to interpret the model's decision, would that be enough? Is the provided explanation, which is based on AI, is it understandable? How good is it to non-experts especially? As these systems move closer to real-world use, AI needs to be able to explain its decisions in a way people can understand. So this is where our research comes in. We want to combine the strength of deep reinforcement learning with graph neural networks and explainable AI. While RL handles the decision making, GNN offer a way to process graph structured data, which is particularly useful in routing scenarios as they can be modeled as a graph. And XAI ensures transparency by providing clear explanations for the model's decisions. For this, we checked the gap in research, and this is what we found. There is actually a lack of integration of XAI for VRP, and there is a lack of comparative analysis to evaluate how different DRL models perform to help identify the strengths and weaknesses of each model. Third, the combination of DRL, GNN, and XAI has not been thoroughly explored, especially in the context of vehicle routing. And finally, many studies remain theoretical, so there is a gap in the real-world application. Especially for us, we own a real-world dataset. So if we want to tackle the gap in research, how do we do that? Our research aims to conduct a comparative study of various DRL models integrated with GNN and XAI. We will evaluate their performance in optimizing routes and how well each model explains its decisions. Our methodology to achieve this is the initial model development to tackle EVRP using DRL and GNN, and then the integration of XAI techniques for interpretability. Different DRL models have different strengths and weaknesses, so we want to evaluate both performance, how well each model solves the EVRP, and how well XAI explains the model's decisions. So our key contributions to this research include first, the interpretable and optimized models for EVRP leveraging DRL, GNN, and XAI techniques, the comparative analysis of these various models, and we want to evaluate both the optimization performance of each model and their interpretability. So what is the impact of this research, feasibility, and ethical concerns?
Now, let's explore the potential impact of this research on both the academic and industrial landscapes. The first key area is advancing sustainable transportation by optimizing electric vehicle routing. We are directly contributing to a reduction in carbon footprints within transportation networks, making fleet operation more energy efficient and supporting industrial transitioning to electrical fleets. Additionally, enhancing AI transparency through explainable AI addresses the challenges posed by the black box nature of AI models. In critical applications like EV fleet routing, this transparency will improve trust and prevent errors by making the AI decision making process understandable. Finally, this research will bridge the gap between reinforcement learning, graph neural network, and explainable AI, offering new insights and creating a framework that could influence future work in both interpretable machine learning and combinatorial optimization. Now that we have seen the impact, let's discuss why this research idea is feasible. We are supported by established tools and resources uh, with mature AI library like PyTorch and TensorFlow and explainability techniques such as CHAP and GradCam, which ensure that our interpretability goals are within reach. Additionally, existing literature provides a solid foundation guiding our direction with previous work on explainable AI, reinforcement learning, and graph neural networks. Then, scalability is another advantage. Starting with a small simulation, we can gradually scale to real world datasets, ensuring that the approach is both adaptable uh, and testable. Now, moving on to the ethical consideration, which are central to any impactful research. First, data privacy is a significant concern, especially when dealing with real-world datasets for electric vehicle routing. To mitigate this, we will ensure that all data is anonymized and follow strict privacy protection protocols. Moreover, by integrating explainable AI, we not only gain technical transparency but also promote ethical transparency, making sure that decisions are clear, understandable, and accountable, particularly in safety critical scenarios like electric vehicle routing. Additionally, the environment impact of this research is significant. By promoting sustainable transportation, and reducing carbon emission through optimized routing for electric vehicle. We aim to contribute positively to global sustainability goals and lessen the environment footprint.
So now let me introduce you to our team who will be working on this research paper. We are a team of 6 members composed of various backgrounds. As the team lead, I, Jimeth, recently completed my PhD in e-mobility and RL, which gave me experience with both EVRP and RL. Eli, our evaluation lead, is currently pursuing his PhD in ML and NLP. Jeremy holds 2 master's degrees in AI and mathematics. So with this his strong technical background, he will serve as the technical lead. We also have Iman, Mam, and Suleiman, who are either master's and undergraduate students specializing in AI. They will be the driving force behind the development and training of our models, working hands-on to bring our solutions to life. Now, this is how each member will contribute to the project in terms of model development, research, and article writing. As the team lead, I will focus on literature review and background research. I will also handle the writing of the introduction, background, and conclusion sections of our final article. Ellie will manage the integration of XAI and conduct performance evaluation and comparison studies of the model. He will also write the sections covering XAI analysis and the discussion, as well as oversee the paper review process. Jeremy will handle the methodology and model design, focusing on problem definition, model selection, and evaluating different architectures. He will also write the models and model implementation sections for the article. Meanwhile, Iman, Mam, and Suleiman will be deeply involved in model development. Each one will focus on implementing and training a combined RLGNN model. So how are we going to make this work?
Let me take you through an exciting journey of our project step by step. So we begin with project initialization and research. The goal here is to establish a solid understanding of deep reinforcement learning, graph neural networks, and explainable AI. During the first 2 weeks, we conduct a literature review, analyze the existing dataset, and finalize the project scope. Next, in week 3, we move to data preparation. We create a robust data set using a publicly available data set and preprocess it. If needed, we also generate a static data. From weeks 4 to 7, we focus on model development. We implement various GRL algorithms and GNN architectures, integrate them, and train model to optimize the electrical vehicle routing problems. So in weeks 8 and 9, we further our models with explainable AI features to make the decision more interpretable. We develop methods to explain models, output, and test the features. So by weeks 10 and 11, it's time to evaluate performance on explainability. We define performance metrics, conduct experiment, and analyze the result. In week 12, we ensure our models are scalable and efficient, optimizing them for computational efficiency and testing across different scenarios. We then move to weeks 15 and 14, where we prepare comprehensive documentation. This includes writing a detailed report on our findings, as well as setting up code repository and manuals. Finally, in week 15, we present our research finds, we demonstrate the model, share our results, and collect feedback to improve our models. Thank you.
Of course, this presentation is built upon a foundation of existing research, and these are the references we used. To conclude, I want to emphasize that together we have the power to not just solve the problems but redefine the future of sustainable transport. The road to innovation is not just about reaching a destination, it's about making the journey smarter, greener, and more understandable for everyone. So let us drive change forward, one decision at a time. And thank you for your attention.